For problem 2, we are asked to determine the source current. Here we have two loads. We have the complex power of each load and the power factor for each one. So to obtain the source current, we need to understand what is the current of each of these loads, or in other way, we can first understand the total power here and then obtain the source current. For this sake, first we need to calculate the active and reactive power for each of these two loads. S is 700 kilovolt ampere here, and we have the power factor which is 0.8 lagging. So we can easily understand that active power is 700 multiplied by 0.8, which is 560 kilowatt here, and the reactive power can be obtained by multiplying the apparent power and the sine of the angle that caused this power factor, or as an alternative way we can write S multiplied by 1 minus 0.8 square, and this value is equal to sine of theta 1, which is the same as this one. Using the same approach, we can calculate P2 and Q2 for this one. 800 multiplied by 0.9 gives 720 kilowatt for P2, and using this approach, or the one that we used for the last one here, we can obtain Q2 as well. Finally, we just need to add these two values together to obtain the total consumed power, which must be equal to the generated power. So we can understand that the total power, which is 1280 plus J 768 kilovolt ampere, as the source power. Then we can use this formula that we also used for problem 1 to obtain the current. We have the source power, we have voltage, and only we need this current. The voltage at the source side is given to be 13.8 kilovolts. This is line voltage, so we have to divide it by root square of 3, which gives us 7.97 kilovolt, which is our source phase voltage, because in this formula voltage and current, both of them are phase values. So after that we can just substitute the values and obtain the source current. Just to emphasize, we have to consider this conjugate sign here. So since we have assumed that this voltage has 0 degrees angle, so we can just write S conjugate over 3V, and after that we can easily find the current here. After that, for part B, we have to calculate the overall power factor of all the loads. Well, we had calculated the overall power, so we can easily find the power factor. We can use the definition of the power factor, which is cosine of theta, or equivalently active power divided by apparent power. Here we have used the first approach or we can use the second approach, which gives us 1280 divided by 1493, which gives the same value, and it is lagging because this is positive, actually, because the current is lagging the voltage. And for part C, which is very important, and we had a lot of people who had some problems here for calculating C, we have to determine the wire connected capacitors in microfarad required to change the overall power factor for all loads to be 0.9, again lagging. For this case, as I just said, PF is P divided by S. We are supplying these two loads using this power source. So when we're going to add a capacitor here, this capacitor can change the reactive power but cannot do anything with the active power. So this active power is constant. But we can change this apparent power because we can inject some reactive power here. The power factor was 0.85 here, but we need the power factor to be 0.9. So we have to increase this value. Since we cannot increase P, we have to reduce S. For this sake, we have to inject some reactive power here to be able to reduce the reactive power generated by the source side, because this S that we had calculated was the S supplied by the source, and also we had these two loads. So we have S load, SC, and S source. And it is clear that a source is, or maybe it's better to say S load is equal to a source plus SC. Okay, for the new power factor, we can write 0.9 should be P, which is constant, and we had it here, 1280 divided by S. This new S is the source apparent power after installing this capacitor. So we don't know what is this S. We can easily calculate it here. S would be 1280 divided by 0.9. We have it here. So after calculating this, also we can write Q, or new Q, new reactive power, will be this S, which is, let's calculate it here, 280 by 9, sorry, 0.9. What was the value again? 1422. That is 1422. So Q would be 1422 square minus 1280 square, which will be this value, 619.9. Before that, we had calculated the reactive power to be 768 kilovolt ampere, but now it is 619. So this reactive power difference must be compensated by the capacitor. So we can write that the capacitor reactive power is this reactive power difference, which is 768.7 minus 619.9, which gives us the new value which belongs to the capacitor reactive power. After that, we know that impedance is voltage square divided by the power, or for this case, because it is only reactive power, we can write X is equal to V squared divided by Q. And the only point is that we have to use phase voltage here and single line reactive power here. So we have to divide this value by 3 and divide the voltage by the square root of 3, or this value that we had calculated before. After that, everything is very simple because we know that the reactance of the capacitor is 1 by j omega c, or if we want the value, we just ignore j because we're calculating the value. And after that, we have the frequency 60 Hz, so we can just substitute the values, and finally we get the C, or the capacitor value, to be 2 microfarad.